Hello there. Let's do topologies and documentation as they're closely related to each other. First of all, let's check out some topologies. Now here are the types of topologies that you are expected to recognize in CompTIA's Network Plus. The bus topology, the ring, the star, the tree, both full and partial meshing, point-to-point and point-to-multipoint, as well as a hybrid of them all. So let's start out with the bus topology. Now we saw this in a previous video where I dealt with CSMA/CD. Originally it was just a bunch of computers connected together via a common network cable. Usually that cable was coaxial, and we called it the bus topology because it does resemble a bus line or a bus route, where there are distinctive stop and starting points in the topology, namely these computers. Now the problem with this type of topology is it was just a network media. There were no devices in the middle to give any sort of intelligent forwarding decisions, and this led to bus topologies only ever being able to run at half duplex or one person talking at a time. This is now considered a legacy media, but you may still come across this from time to time, and there are some unusual implementations of it in modern networking. Then, an attempt to improve the predictability and controllability of communications was the ring topology, where we'd have all the computers we wanted to connect to the network connected together in essentially a ring. Each device would have two network cards and would connect to its immediate neighbors. Now, again, this is also a legacy style of network media, so you're unlikely to come across it anymore. But it used to run with something called token ring, which was a layer 2 service that allowed for control of who spoke when. The devices would have this thing called a token that they passed around between each other. And if you had the token, you were allowed to put your message on the network. And what would happen is, if this device had the token, it would send its message out of one of its interfaces, let's say this one, and it would make its way around the network. And eventually, it would get back to this device on the other interface. And that's how this device knew the traffic had got around the network. It would then release the token onto the next device to have its turn. Now, the way it would be confident that the traffic got delivered is that, well, the recipient was hopefully in the ring. And if the recipient was not in this ring, there usually would be a router connected somewhere here that would route the traffic to another network if the recipient was elsewhere. But nonetheless, though, the sender would be confident their message got to the recipient somehow because they got their own message back. The problems, though, that the ring topology has is, as the ring gets bigger, you have to wait longer and longer before you get your turn with the token again. Add to that as well, if the ring gets broken, you are going to have a problem. And Token Ring tried to address this in several ways, where it would try and bounce the traffic back, or introducing a second ring. But ultimately, this still had the same problem of just computers and media. There were no intelligent network appliances anywhere to be found. But we started to get that when we started to encounter the star topology, which is something you can expect to see in modern networks. Now, the star topology, what ends up happening is you're going to have a central network appliance like a switch, and everybody connected to it, forming a star. Now, obviously, this is going to have a limit because the switch only has so many interfaces. But you can have extended star topologies where you have loads of devices like multiple switches and routers and many endpoints, all connecting together in one bigger star. And if you're looking at this thinking this looks very similar to a modern network, yes, you're right. A lot of modern networks do use star topology elements or are fully star. Now, a very common thing you'll see is a tree topology, where you'll have this tree-like hierarchy of appliances connected together. Now, the idea would be that we would probably have down here low performance switches providing access to many users. We consider these computers to be the leaves of the tree, and these to be the branches, the twigs, the trunks, and all of that stuff leading to the root somewhere, which is more than likely a router. Now, what's quite neat about this topology is we would have quite a lot of fairly cheap, moderate level, maybe even low level performance, depending on how you look at them, switches. And then at this level, we would have moderately good, medium, middle of the road performance switches. And then over here, we'd have a core switch, or multiple core switches that are very high performance, probably quite expensive, but very, very capable. Now, depending on which network vendor you get into, they normally give these three layers of a tree topology a name. So a lot of them will call this area here the core layer. Well, this layer over here, you'll see network vendors normally referring to it as either a distribution layer or an aggregation layer or something similar. And this layer is almost always guaranteed to be known as the access layer, as this is where users get access. Either desktops with their network cables or wireless access points would be plugged into these switches. And the idea is to balance the number of switches, the performance and stuff like that, to try and get a good manageable network design. But similar to the star topology, it has a glaring weakness, and that is there is not much redundancy here. So if anything were to go wrong with any of these connections or devices, we would have a partial or even a complete network outage, which is obviously not desirable. So to achieve redundancy, we introduce meshing. Now the full mesh, what's going to happen is you're going to have a bunch of nodes and they're going to be connected to each other. The definition of a mesh is that every node, and this means any device that can actually communicate on the network, gets a connection to every other node. Now over here we've got 4 nodes, but we've got 6 connections. If we added a 5th node, we'd land up with 10 connections. If we added a 6th node, we'd land up with 15 connections. Every time I add an extra node, the number of connections I now need to add to this network grows a little bit exponentially. Thankfully though, we have a formula to predict how bad it can get if we go full mesh everywhere. The number of connections is equal to the number of nodes multiplied by the number of nodes minus 1, all divided by 2. And if you try this out, you will see you can get a crazy number of connections you need to set up and maintain to have a true full mesh. But with a true full mesh, what happens is you've got redundant connectivity for days. If anything does go wrong with any of these nodes or connections, there will be a way around that failure. But then we get the partial mesh, where you choose to put redundancy where it makes sense to you and not put the redundancy where it's not going to be beneficial. So for instance, if I took that tree topology from earlier, I'll probably introduce some partial meshing between the switches, but not down to the end users. Because if one person can't get onto the network, don't get me wrong, it's a problem we need to fix. But it's not nearly as bad as dozens or hundreds of people being unable to communicate. So it generally makes more sense to do redundancy and meshing partial between network appliances rather than to end devices. Then we get point-to-point, which is a very self-explanatory type of topology. You've got 2 devices, each representing the point, and they're directly connected to each other with pretty much nothing else going on in between them. Now it's a bit weird to have 2 PCs point-to-point, so what you're likely to see is routers having point-to-point connectivity, or even entire locations or sites as represented by these 2 little fluffy clouds being connected to each other, making for a logical point-to-point. This only helps though if you've got 2 sites. If you've got more than 2 sites and you want to connect them like this, then you need to look at a point-to-multipoint topology. We have one central point and then multiple points that all connect to that one central one. And if these were not routers and rather sites, basically this would probably be head office and these would probably be branch locations. Now realistically, what you are likely to encounter when looking at your organization's network is a hybrid topology, where there's a bit of everything going on. A bit of tree, a bit of partial meshing, maybe even a bit of point-to-point or point-to-multipoint if I include different sites here. But essentially we have the different topologies, each forming part of this network infrastructure depending on how much you look at it. If I just look at these switches and their connections between each other, we've almost got a full mesh. We just needed a connection straight from that switch to that switch. Definitely partial meshing down here, and these guys might treat their access switches as a star. It all depends on how close you want to zoom in to the network and analyze it from there. I mean, for instance, if I zoom in over here, this looks like a star topology. But then if we zoom in over here, we start seeing partial meshing. Now, topologies discussed, let's talk about documenting it all. Because network documentation is massively important, and I've got bad news for you if you haven't had any time in the industry yet. Very rarely well maintained. So let's try and fix that. So documentation is meant to help support us with regards to things like troubleshooting, consistent network deployment, because if we are able to refer to documentation, we can continue deploying and expanding the network in the current design methodology and ethos that has been followed up until this point. It also helps us do capacity planning for the future, because we can work out where our network might start running into problems, and we can expand upon it before we start having issues and performance problems. And it helps staff members, especially new ones, get up to speed with regards to supporting this network, because they can then look at the topology diagrams, configuration information, and so forth, and be much better equipped to support and help the users. Now, because of this, we've got several types of documentation that we need to look at. First and foremost is config management, something that is super useful and helpful, but not always done very well, if at all. Then backup management, because he who laughs last probably made a backup. Then change management documentation helps out a lot, as well as asset management, and then finally some documentation for network management. So let's look at the config management first. Configuration management is all about tracking how something is configured, documenting that, and storing that. And what we're going to have to do is we're going to have to first identify something called a service asset. Service assets are basically the things that are providing the services across the network that the users are wanting. Then we're going to develop a management plan for configuration items or configurable items, whichever term you prefer. These are the network appliances and resources that we set up, configure to deliver the service assets to the end users. And it's basically the router, the switch, the wireless access point, etc., and how they are configured that we want to be managing, documenting, and storing somewhere. One of the cool things we can do, though, once we've started doing configuration management, maintaining knowledge of current configurations and stuff like that, is we can start monitoring for something called config drift, where something gets altered, changed, or adjusted, either for troubleshooting or change management, and isn't properly documented. Now, configuration drift itself is not bad, but we do need to know it's happening to work out, was this an intentional configuration change, or was this something we did in a bit of a hurry for troubleshooting and could lead to problems further down the line. Now, besides looking for the configuration drift, configuration management can be amazingly useful for troubleshooting. As a very common thing to ask, a very good piece of advice for troubleshooting is what has changed since it last worked. And in networking, this is a very, very useful thing to look for, because usually the network is very, very stable until someone goes and changes something. If we can figure out what that thing that was changed is, we could probably figure out how to fix it. Now, I would suggest that you consider getting a configuration management system to help you document and track your configurable items and your service assets. And take advantage of a configuration management system's ability to also store several versions of an appliance's configuration, so you can backtrack when a change might have occurred historically that has led to a problem now. Because maybe the problem started right when the change happened, but it only started becoming symptomatic and noticeable to you and your users now. So it's always good to be able to dive into the past of configuration of your appliances. Then, let's talk about backup management. We all know backups are important, but we don't like doing them. But still, we must do it. First and foremost, you want to document your backup procedures. One of the first things to start with would be a backup policy that outlines that backups must be done, how they should be done in general, what should be backed up, and stuff like that. And then we want to have a regular schedule being followed. Again, the policy can help enforce this. Because if we can do backups regularly, that means we can be pretty certain about when we need to recover and how up to date the data would be. To make a regular backup schedule easier to do, I highly suggest automation. Whether that be through a backup utility or through a little bit of scripting of your own, I'm not too worried, but definitely make sure that you do backups regularly. Another good idea is to make sure that backups are part of regular changes. If you're about to do a change, do a backup. Once the change is successful, do another backup. Believe you me, no one has ever said, "Oh wow, we've done too many backups." I have never had anybody ever say that to me. Another important thing to do with your backup management as well is to verify them. If you are automating your backups, you want to verify that they are taking place and are being successfully done. And if you're doing it manually, you also want to just double check that file sizes are correct and it all looks a-okay. Another thing you want to do for verification is to check that you can use them in a recovery. A very dangerous thing that you could do when it comes to backups is assume you'll figure out how to use them in a recovery when you need to. That's dangerous because now you've got pressure and you're doing something for the first time. You want to test your backups with a test recovery operation, even in a lab environment or something like that, just so that you can be sure that if you need to do that recovery at some point in the future, number one, you know your backups will work for the recovery. Number two, you've practiced doing it. You are more familiar with it. So if it ever happens, you have experienced it, you've gone through it, it's not the first time that you are now figuring out how to use a recovery tool. Trust me on this, it'll pay dividends in the future. Then comes a term that most IT professionals dread hearing, change management, although sometimes it's referred to as change control now, but overall they're very similar concepts. The idea is that a change is any alteration to an IT system that can affect service delivery and value generation. Now, when I say any alteration, I mean adding something, updating something, reconfiguring something, removing something, decommissioning, anything that affects how the IT environment operates is considered a change. And there are multiple frameworks that you can follow when it comes to change management. But most of them include common aspects like submitting a change proposal to a change advisory board, saying, hey, here's something we want to do, whether it be adding or removing something. Here's our motivations for why we want to do it. Here are the risks of not doing it. Here are the risks of doing it. Whole bunch of motivations, as well as how you're going to do it, what your backup plan is going to be, which we'll get to in a moment, stuff like that. You're going to have a proposal that you put forward, and that change will then be approved by some sort of approval body. Now, one of the most key aspects to a good change, besides obviously a solid method for implementing it, is an even more solid method for backing out of a change if it starts going bad. Because you're going to have to do your changes sometimes during scheduled periods of maintenance, or during change windows that are set up specifically to do a change and are completely outside of your maintenance windows. And if you are unable to effect your change in time, you need to be able to back out and revert to how the system was just before the change was initiated. Essentially, the backup plan is to make sure that whatever you do, you don't make a worse situation than what you were trying to improve. And then documentation and updating that documentation to ensure that every time you do a change, the supporting documentation that we rely upon for planning and troubleshooting is updated to reflect the new things going on in the network or the alterations that have been done. And ideally, you want to tie this into configuration management so that you know that your config management system contains very up-to-date information about your configurable items. Then, asset management or asset inventories. Both terms are acceptable. You want to make sure you are regularly reviewing this inventory because it's one of the things that tends to get neglected a lot by many IT departments. Not keeping track of the devices as an organization you have purchased, where you've implemented them, who you've allocated them to if it's an end-user device, stuff like that. Very, very poorly maintained by many an organization. Let's try and fix that by making sure we review it and see if we can find any things that have not been added to it. Also, if you make updating of your inventory part of your change management, it's going to be a lot easier to keep this up to date. Also, when you acquire new equipment and devices, make part of the initial unboxing and allocation process updating the asset inventory. You want to make sure that you record particular details such as a description of the device, the purchase date and the warranty period, service history, or if you can't fit this into your asset management records, then at least a reference to wherever the service history can be found, the device's status, its location, and if we're talking about end-user devices, then who got allocated to. I would highly encourage that you investigate a good asset management tool or asset inventory database to make this a much easier thing to do. Then comes network management. Now, network management documentation often comes in the form of network diagrams. A very, very popular method of documenting your network. So generally we go with two main types, physical network diagrams and logical network diagrams. Let's tackle the physical ones first. So interconnection diagrams that track how different devices physically interconnect to each other can be super useful. But it might not be great if you don't know where the device is. So a good idea after creating the interconnection diagram is to overlay it on top of a floor plan and move the devices around to represent where they are in the building. And then when it comes to the server room or network cabinets that are significantly large, a rack diagram would be very useful so we know which device sits where in the network or server cabinet. Even if you have gone and labeled these devices, don't trust those labels to stay forever. They might peel off, they might fall off. Sometimes if it's a thermal label, they might fade. So do a rack diagram as well so that you can always go and count, ooh, it's 6 devices from the top that I'm looking for. There we go, that's the switch I need to fix. Or there's the router we need to upgrade the network card on. Then we'll have logical network diagrams. These will usually cover things like the protocols we're using, the services that run across the network and where they're set up at, and details about how those services are configured on the servers themselves. We'll do data flow diagrams to track how data moves. We'll do address usage diagrams. You name it, you can come up with it. And don't limit yourself to what you're seeing in this video or in CompTIA's Network Plus course material. If you go to a workplace and they've got a type of network diagram that you haven't encountered before, check it out, work out, does it add value? More than likely it does, and go with it. There is always a way that people would like to see the network diagrammed, configured, tracked, whatever. That can be very, very useful in a particular type of organization that would not necessarily be useful in others. My video and CompTIA's Network Plus material is trying to be good for everybody but perfect for no one in particular. We're trying to cover as many bases as we can while still making sure that your skills are useful at all organizations. It's a fun balancing act. Now, make sure that you use multiple diagrams for larger networks. As trying to fit everything into a single diagram when you're dealing with very large networks where you might have hundreds of appliances and thousands of endpoints or nodes, it's going to be very, very difficult to have a fully representative and detailed diagram that shows you the whole picture. So maybe do a summarized full view of the network, and then you do more details in a segmented view, where you zoom into a particular LAN segment and you might show individual connections to nodes. Whereas in the summarized view, you might just have something that represents the dozens or hundreds of clients that might be in that particular LAN segment. And then don't be afraid to use less visual forms of documentation. Like for instance, with IP addressing, you might want to use a table to track the allocation of IP subnets. Anything that helps you track and document how the network is configured will be useful, especially if you keep it up to date. Now, in terms of tools to help you with all of this, let's look at host and network discovery. So first, we want to do this type of thing to try and validate if the documentation is accurate or not. And if it isn't, we can use the tool's results to help us update our documentation. Now, some of the tools we'll look at here might be also used in security assessments. So that's cool. But any tool that's classified as host and network discovery will usually be aimed at identifying the devices on your network, the services running through them, and if it's the kind of tool that would be used for cybersecurity, any security gaps that you might have. So a very popular tool for all of this is Nmap. It is available for Windows, Linux, and Mac OS. And what it does is it scans the network and shows quite a lot of results to you. And it can discover a plethora of things. But some of the big things that you'd be most interested in for network administration and just improving your documentation would be what IP addresses are in use in that network, the open and or responding port numbers on those particular systems. You can even pull host operating system details and so much more. If you want to get an idea of what Nmap's capable of, you can go and look at its help file and just see the number of options you have for a scan. It's absolutely mind-boggling. But I do need to give you one big warning. This tool is used by security professionals, network admins, and hackers. And as such, it may accidentally trigger any of your security monitoring tools. So it's best to make sure that you plan and schedule the usage with your security teams, so that if they detect any unusual activity that Nmap would be doing, they don't react to your assessments and checks on the network as though a hacker is coming and doing some reconnaissance, because hackers do like to use Nmap early on in their attacks to learn about your environment. And as such, an organization that's got a well-developed security posture may detect the use of Nmap and react to it. So plan it out, schedule it, stuff like that. But we also have some devices that are able to discover the neighbors on their own. Like for example, Cisco appliances have access to something called CDP, or Cisco Discovery Protocol. It is a proprietary protocol, and it's very good at discovering neighboring devices from Cisco running at OSI layer 2. So even if I haven't set up an IP address or anything like that, CDP allows Cisco devices to discover neighboring Cisco appliances in the network, which is pretty useful. And as such, an open standard alternative called Link Layer Discovery Protocol, or LLDP, was developed by the IEEE. And it can also discover the neighboring appliances running at layer 2, very similar to Cisco, but it does require that all the devices that you have running have got LLDP, and it is set to run by default. Or if not set to run by default, has been enabled. And that will allow you to use LLDP instead of having to rely on buying Cisco appliances. Because as great as Cisco may be, there are other vendors out there. And your organization might be choosing a different vendor for a whole number of different reasons. But seeing as we're onto the open standards, let's talk about SNMP, or the Simple Network Management Protocol, which can help you manage and monitor your network appliances, like your routers, your switches, and your servers. And the way SNMP works is it's a question-answer format, where a server that monitors our network, called the NMS, or the Network Monitoring or Network Management Server, whichever acronym you prefer, is able to send questions to the appliances and say, hey, how are you doing with this particular thing? And they get results or answers back. They provide the details and information that we would like to know. As I said, it's an open standard protocol, so very widely supported. Now, in terms of how SNMP works, like I said, we've got a management or monitoring server called the Network Management/Monitoring Server, NMS. We'll have our network appliance, and running on that network appliance is an executable element called the agent. The agent is going to engage with a data store called the Management Information Base, which has all the configuration settings and performance metrics that you might want to find out about. Whether you want to see how is this particular interface set up, how is this particular protocol being utilized, how saturated is a particular link, in other words, how much traffic's going through it. You name it, we can probably query that through SNMP. Now, the question and response process is SNMP itself, actually. But we do refer to the agent over here as the SNMP agent, but we very seldomly call this the SNMP MIB. It is just the management information base that can be accessed by SNMP and any other protocol like it. Now, the appliances will usually be receiving the SNMP queries on UDP port number 161. The NMS will be running both UDP port 161 for ordinary responses and 162 for a trap message, which is a type of alert. So let's talk about those messages that we are running through SNMP. So first, the questions we ask are referred to as GET requests. These are requests to retrieve data from the agent running on the appliance. And the agent responds to the NMS with something called a GET response, the data from the agent to the NMS. We also have this thing called a GET next request, which allows the NMS to query dynamic information like a full table of data, like a routing table or a MAC address table or something like that. And then for some of the newer versions of SNMP that support configuration, not just monitoring, but also configuration, we have this thing called a SET request, where we send a value to the agent and tell it to write that to the MIB, and that affects a change into the device's configuration, which is pretty cool. It allows us to have indirect remote administration capabilities. And usually the agent will reply to a SET request with a response, sometimes referred to as a SET response, just to validate to the NMS that the setting has been applied. And then we have the trap message, which is, in SNMP terms, an unsolicited message. In other words, the agent sent this to the NMS without the NMS making a query. And this is usually used to alert the NMS to a fault or an alert or some similar problem, without an original GET request or GET next request. Now, the SNMP, there have been several versions over the years. We've got version 1, which I really don't like, because it doesn't really do much for security. It only supports GET requests and GET next requests as well. It doesn't support configuration, and the trap functions were retroactively added to SNMP v1. So with some vendors, they might support trap messages with v1, other vendors might not. Your experience will vary. But generally, I'm not very mad about SNMP v1 being used due to the inherent security problems. SNMP v2 sort of tried to fix this by introducing authentication of the NMS, where the agent will validate, am I talking to the legitimate network monitoring system, or am I talking to a hacker trying to trick me into believing they are my network management system? But it used a couple of other things for encryption that was considered controversial by a lot of people. So the data protection solutions weren't the greatest. But v2 did introduce the trap messaging as well. Although it wasn't very well refined at the time, it is where it started. We now have SNMP v2c, the community-driven version, where they experimentally introduced set requests and pretty much gave us version 2, but they took out the controversial cryptography that version 2 had and went with a more acceptable model. In case you're wondering what's the issue with the cryptography, it's not the best in terms of keeping you secure. You might as well just go clear text because you're adding processing cycles to encrypt traffic that is very easy to crack. If you want to use SNMP properly, I suggest you go for version 3. It does authentication of the NMS. It does proper, good encryption of the transmissions. It supports configuration via set requests properly, although the configuration through version 3 is off by default. It is the better option. Whenever I deploy a network and I have to set up SNMP for that network, I always make sure it's running version 3. If for whatever reason the person says, no, we can't use version 3, my answer is then you're not using SNMP. Version 3 or nothing, as far as I'm concerned. And what I would definitely suggest as well is that you make sure whether it's running or not in your network. Some vendors run SNMP by default as a factory setting, which is not always the greatest because it might be running version 1 by default. The advice is this: if you're going to use it, use version 3. If you're not, don't use it, but check that it's not running by default, because it could be a very dangerous thing if it's running and you don't realize it, because an attacker who gets a rogue device into your network could use this as a way to learn about your network and how it's doing. But SNMP and related protocols are all about, basically, performance monitoring. Now, performance monitoring can be done through a variety of methods and solutions, some of which we will cover in later videos. But generally, we want to try and measure particular things, like the bandwidth of a particular interface, which is the maximum capacity it has. Then, the throughput, a measurement of how much traffic are we actually sending through. Similar to water flowing through a pipe. If I don't open the tap all the way, not all the water goes through the pipe. I'm not taking full advantage of that pipe's width. And networks are very similar to that. If I say I've got a 1 gigabit per second interface, it means my bandwidth is 1 gigabit per second. But whether I'm actually transmitting my data at a gigabit per second all the time, well, that depends on what I'm transmitting. Now, there's also a variation of throughput that CompTIA doesn't officially recognize for the Network Plus exam, but I would like you to know about it anyway. And it's called goodput. Goodput is throughput with successful first-time delivery. Now, if I have a good throughput or a goodput, that means that all I am sending is getting delivered first time successfully. There's no requests for retransmission if it's using TCP. And that is something that's good for us, because I might have a very high throughput, but if a lot of the traffic that's being sent through that link is requests for retransmission, then I'm not really getting that much data through, because I'm sending the same thing over and over and over, which is a waste of the network's processing capacity and the human's time. Another thing we also might want to measure would be transmission latency. How long it takes for the data to get from me to the recipient in seconds. Now, the cool thing about transmission latency is it factors in things like the processing of the various headers, as well as the payload data. And this can be much more reflective of what your network's overall performance feels like. Then, other interesting thing to monitor would be the appliance's CPU and memory usage, because yes, your routers, your switches, etc., they're just miniature computers that specialize in one thing and one thing specifically, their particular network function. And as such, being miniature computers that are hyper specialized, they've got CPU, they've got memory, and we want to keep an eye on how heavily utilized they are. You also want to keep an eye on the appliance's storage. Most of your network appliances have some sort of internal flash-based storage that is not that large in terms of capacity. You might have a couple hundred megabytes, maybe even a couple gigabytes. but very seldomly more than that. Remember, routers, switches, wireless access points, and even firewalls to an extent, are not meant to be file storage servers, so they're not going to come with a large amount of storage, which means that if you are not careful, you can fill that up very quickly. And if you've ever had full storage on your smartphone, you know it plays up on you sometimes when that happens. So we want to make sure we keep an eye on the storage usage and free it up if it starts getting a bit heavy. Now, a very good thing to do with performance monitoring of any kind is to have baselines. The idea of a baseline is it's a measure of known good. And it helps us when doing performance monitoring to compare the current performance to the baseline. Because then we can see, yes, the network seems to be behaving itself, it seems to be performing in expectations, or we can identify problems when it doesn't match up with a baseline, or at least within a margin of error. Now, one key thing to do when measuring your baselines and saving them is to also note the context of the baseline. When you did it, what time of the year, what time of the day, what was going on in the workplace at the time, stuff like that. If I do a baseline over some sort of holiday season, the network's going to be a lot quieter than during a more normal time of the year. If I do a baseline on the finance network during pay cycle, it's going to be way busier than outside of pay cycle. So we do need to make a note of the time and the activities that were going on in the organization so that our baselines have the context, and then when I'm doing a measurement at some point in the future, I can make sure I'm using the appropriate baseline to understand and compare my performance to. Once we have that, then we can start developing threshold alerts, where performance may exceed particular values, either going above or going below, and we get a notification about that. Now, we do want to use a bit of a combination of metrics being exceeded for periods of time to minimize unnecessary alerts. So, for instance, if a particular network appliance's CPU hits 90% utilization, that happens surprisingly often. So maybe I would rather have it hitting 90% utilization and staying above 90% for 5 minutes straight. Then I get an alert, because now we've got a condition that is persistent and worth my attention. Maybe I do the same for the throughput. If the throughput goes down bad, but stays down for like 10 minutes, half an hour or something like that, then I might want to be alerted, because occasionally things will happen that cause the throughput of a connection to drop and then come back up again. But if it drops and stays down for a long period of time, that you might want to know about. But we'll touch on some of the other cool tools that you can use for performance monitoring in their more relevant videos. But for now, that covered the basis of topologies and documentation. I'd like to say thank you for watching. I really appreciate it. And if you have any friends, family members, colleagues, or peers that would like to also do Network Plus, don't be afraid to share this video with them. Otherwise, though, I will catch you in the next video.